Good morning, everyone. Thank you for taking our time in attending this session. We understand it's a weekend, and hence we'll try our best to keep it interesting. I'd like to also thank the organizers of this meetup, Nishit, Safir, and Abhishek, for this opportunity to present and for hosting us today. Quickly moving on to today's topic of discussion, a mighty elephant's journey to the cloud. As our title suggests, the elephant in the room is Hadoop, and we are going to give you some insights into Twitter's current Hadoop infra and address the whys and hows of Hadoop's journey to cloud, and which we at Twitter fondly call partly cloudy. So yes, that's us. So I'm Abhishek. I work as a SRE in the data platform team. Likewise, with us, we have Jeffrey, who's my colleague, and both of us would be presenting today's topic. Before we get onto the main context, I'd like to get some pulse on how many folks here have some experience on basic knowledge of Hadoop or GCP. Please feel free to use your Q&A box for that. And and don't worry, Hadoop knowledge isn't a prerequisite for this session. So we will cover Hadoop basics for a couple of minutes before we move on to a Twitter specific Hadoop infrastructure. Okay, to start off with, we're going to talk about the infrastructure workloads we have at Twitter, followed by a quick intro to Hadoop, and later discuss the current Hadoop architecture, and finally move on to talk about Twitter's journey and challenges we faced during our migration to cloud. And finally, towards the end, we will open up the session for any Q&A. So please feel free to shoot your questions at us, and we will be more than happy to answer them all. So coming back at Twitter infrastructure workloads. So considering Twitter's unique scale and performance requirements, we run different types of workloads, which include, but not limited to, as mentioned below. For real-time processing, we have Apache Heron, which is a distributed stream processing engine developed at Twitter and later open sourced, which is a successor of Apache Storm. And coming to key value stores, we use Manhattan, which is a real-time multi-tenant distributed database, which serves as backend for tweets, DMs, etc. And on the messaging queue side, we use Kafka, which is an open source PubSub and a distributed message queuing system. We use, in terms of databases, we use MySQL, Vertica for big data analytics, Postgres, SQL, and Druid, Druid for high performance real-time analytics. On the general computing side, we use Apache Mesos heavily for the compute clusters, and Apache Aurora, which is a scheduler for Apache Mesos. Talking about real-time querying, so we have Presto, which is an open source distributed SQL query engine for running interactive analytic queries, right? And for Hive, which is a data warehouse that provides SQL-like interface. Zeppelin, again, is an open web-based notebook that enables interactive data analytics. BigQuery is an enterprise data warehouse by Google, which we've recently started using. We're going to talk about this a little later onto the slides. And batch computing. For batch computing, we use Hadoop, on top of which we run scalding jobs. Yeah, so scalding essentially means map-reduce jobs which are written in Scala. So hence the name scalding. So before we start talking about Twitter-specific Hadoop architecture, right, in the best interest of everyone attending this session, let's just quickly go over a brief introduction to Hadoop, its components, and core principles. So what is Hadoop? Hadoop is an open source distributed processing framework for big data. Okay, we spoke about big data. So how big is big here? We're talking about data sizes in the order of magnitude of TBs and PBs, that is terabytes and petabytes. And that's when the power of Hadoop truly kicks in, right? Now, talking about the components of Hadoop, HDFS, which stands for Hadoop Distributed File System, is the storage component of Hadoop that conveniently runs on commodity hardware for processing distributed data. Then we have Yarn, which is the compute layer, which stands for yet another resource negotiator, which facilitates data processing on top of HDFS. Coming to the application layer, these are nothing but the scalding jobs that I just spoke about, are the Spark jobs, which are basically the core of MapReduce applications that run on top of HDFS. So what are the core principles of Hadoop? As I mentioned previously, the true power of Hadoop is reflected when the data size in the order of TBs and PBs. And the data is distributed into tens and thousands of servers. So data is mostly split into 128 MB block sizes, which is much larger as compared to the Linux system, where the block size is just a few KBs, like 4 KB, right? The reason of having this huge block size is to minimize the cost of disk seek and reduce the metadata information generated per block. And Hadoop scales linearly with the number of nodes added. So hence it's horizontally scalable. And on HDFS, the data is stored in multiple locations, of course, based on the replication factor. And in any event of one storage location failing to provide the required data, the same data can be easily fetched from another location, hence justifying its fault tolerance and self-healing. And Hadoop runs on commodity hardware, which makes it way cheaper compared to any traditional databases out there. So what is Hadoop used for at Twitter? So yeah, as the slide says, a lot of things. So for batch data processing, event log pipeline, ad hoc jobs and queries. So just to talk about what ad hoc jobs and queries we're talking about, it refers to running one-off queries or a MapReduce job. For example, if I want to see how a specific ad campaign is performing compared to the last 4 campaigns, like I want to just quickly pull up some data from there. So that's me running ad hoc job or query, right? And of course, distributing software with Packer and low latency querying analysis of data with Presto, Hive, Zeppelin, and BigQuery. We also use it heavily for backup or storage. We call it the cold clusters, and yeah, many more things. So let's look at some interesting stats that shows the scale at which we operate Hadoop at Twitter. We have more than 500,000 of compute cores, more than 500 petabytes of unreplicated logical storage, peak cluster size of 12,500 nodes. We have multiple such clusters, greater than 1.5 terabyte or trillion of messages events per day. And just to restate the fact that these stats only depict data for Hadoop and not the whole of Twitter. So yeah, let's talk a little about Hadoop architecture before Partly Cloudy, which was purely on-prem. The little blue birds on the left are the users who are tweeting, retweeting, and having conversations on Twitter. All of these user actions generate data, and this data is collected by our log pipeline, and it writes to real-time clusters and streaming systems, such as Apache Heron, based on the event type. All of these in the real-time clusters, right? So data is collected, aggregated, processed, and also order time partitions are created and then replicated to the production clusters. So production clusters are clusters where the core production periodic jobs are run based on the business logic and requirements. And eventually the data sets end up in the cold storage and also other destinations such as HBase, which is a non-relational distributed database. The ad hoc clusters, as I already mentioned, is used to run off one-off ad hoc queries. And at each phase, new data sets might be created based on the business logic. Also, just to add to that, at Twitter, we use namespace federation and VueFS, which are client-side mountables that not only help us scale the worker or data nodes, but also help us scale the name nodes, which is the brain of Hadoop, very efficiently, which we would talk in detail in the later slides. So what is Partly Cloudy? I mean, why Partly Cloudy, why GCP, and why not other cloud service providers, right? We're going to look at it right here. So what is Partly Cloudy? A project to extend data processing like at Twitter from on-premises only model to hybrid on-premises and cloud model. So we strategically plan to move only Hadoop's cloud to the cloud, only cold clusters and ad hoc clusters to GCP. And why Partly Cloudy? It was our long-term plan to have some cloud presence and become a hybrid platform. So a right strategy will balance the developer agility, capabilities, and enable more dynamics to scale up ad hoc Hadoop compute resources. But why GCP and why not other cloud service providers. We evaluated various cloud services in mid 2016, and for data platform specific workloads. So just let me restate, for data platform specific workloads, GCP provided high performance networking and strong scalable compute and storage platforms. So more importantly, access to other Google offerings such as BigQuery, Cloud ML, and Cloud Data Flow was also a major decision factor. Hence, after a very careful evaluation, the leadership at Twitter strategically made the choice considering GCP's strong set of product suite and customized solutions. The evaluation included running various rigorous benchmarking tests such as GridMix.io, TerraGen, TerraSort. We wouldn't be going into further details on the evaluation process, but having said that, towards the end of the presentation, we also have added a link to Twitter's external talks that provides an in-depth reasoning as to how GCP was a big win for us. So please feel free to take a look at that. So this was all about, the previous slide was all about Partly Cloudy, what was Partly Cloudy and why GCP, right? Now we're going to look at why Hadoop in specific. Since Hadoop is an open source software, it is separable with lesser dependencies. Even though it was not an easy lift and shift for us, re-architecting was still achievable. We ran 2 independent financial models and found the long-term price to performance curve looked to be kind of reasonable. Hadoop offered several important specific benefits, all with lower risk. Scale, we were able to scale compute and storage dimensions independently, which was a huge boost for Hadoop to be chosen as a workload to be migrated to the cloud. This is my favorite slide, actually. So it's now time that we talk about the Partly Cloudy project, the journey, and we'll try and share the challenges we faced during the migration. And I also would pull up a nice tweet from Shahrukh from last year. So let's try and answer Shahrukh's question and maybe later tag him in a tweet once we have the recording out. So moving on, let's take a look at how the architecture changes for Partly Cloudy. Let me just, yeah. So let's just take a look as how the architecture changes for Partly Cloudy. The ad hoc clusters have moved from on-premises to GCP. The data storage is now in GCS, that is Google Cloud Storage. And we have introduced a new component called the copy cluster on-premises. If you observe the blue box towards the end, right? The copy cluster has the sole functionality of replicating data from on-premises to GCS. We don't run any general purpose jobs on this cluster. The nodes on this cluster has connectivity to Twitter internal systems as well as to GCS. Okay, so you might have a question is like, why are we why is all this fuss around copy clusters, right? So the reason we set up that copy cluster is to restrict the blast radius of the number of nodes on premises that will have access to public cloud. Having said that, it's also important to note that that connection between the blue box that you can see, right, the copy cluster to Google Cloud Storage, so those GCS buckets goes over an approximately 1,000 Gbps a private peer network with Google that we have. It's PNI, private network interconnection. Yeah, we would speak about more of it in the later slides. So up until here, the talk was all about addressing the whats and whys of Partly Cloudy. Jeffrey would now talk about the approaches we took and the challenges we faced during the cloud migration. Over to you, Jeffrey.
Thank you, Abhishek. Hello, everybody. I am Jeffrey, and I also work in the data platform SRE team at Twitter. Okay, so continuing with the talk, the Partly Cloudy architecture was driven by basically 4 design principles. The first one is we needed everything to be secure out of the box. So AAA, that is authentication, authorization, and audit was needed, and it was needed to be properly built in, and enforced seamlessly to users. Because we have on-prem users, we've been running on-prem clusters for a long time, and the security principles that were applied there needed to be seamlessly integrated into the cloud environment. Otherwise, it would be a lot of work for our users to readapt everything. So we needed Kerberos for authentication, LDAP for authorization, as well as we needed to implement auditing so that we could reinvestigate stuff, go back and replay what happened, everything, not just as part of security investigations, but also as part of analyzing our usage and all other aspects. So then GDPR compliance is a big thing, and its requirements with respect to storage of data, retention of data, and what should not be included in stored data, like personally identifiable information, had to be adhered to. Then PDP, that is privacy and data protection, that stemmed out of compliance requirements and the basic right approach of securing your data, especially for an organization like Twitter that was handles a large volume of data. The second principle was was regards to making it easy for users to onboard onto our services and properly monitor and track their usage. So delegated resource management needed to be part of that. And the third principle was the principle of least privilege access. Data, compute, and network, all these components use different methods for least privilege access. And those needed to be, whatever we implemented, it needed to be modern, in sync with up-to-date standards that were used by the industry. And the fourth principle was that of incremental development, because there were a lot of components in play. We had to approach, validating and testing each component step by step, so to ensure that when we finally got there, everything that was implemented was secure, was reliable, and was running properly. Next, let us see what the Hadoop stack in cloud had to be based on these principles. So on-prem, we were using HRaven for collection of metrics, storage of metrics, job history, all those information, and providing it to our consumers. But in cloud, we had to implement ATS V2, its application timeline server V2, which is another, which is a new and modern implementation of metrics collection that Twitter itself has worked a lot in bringing out. It is open source, and so we have our own developers working on integrations, and we push a lot of stuff to the open source community. Then with regards to authentication, authorization, audit, Kerberos was needed because that is the secure way of implementing Hadoop clusters. For deployment, we needed to use Google Deployment Manager and Puppet 5. The Hadoop's version had to be 2.9, otherwise we couldn't implement Kerberos or a lot of the newest stuff. So as consequently from Hadoop 2.9, to run Hadoop 2.9 efficiently, we needed to upgrade JDK kit to 8 as well. And obviously, operating system-wise, CentOS 7 had to be the version we went for. And kernel-wise, we needed kernel 4.x. So when it came to hardware, we needed to be able to, our Hadoop versions and everything, and what we deployed had to be properly validated to run both in Twitter hardware as well as in the Google VMs. And the physical infrastructure would now be spread across Twitter as well as the Google data centers. Yeah, so let's now move on to the approach we decided to follow in putting this design in place. So one of the approaches was all the data had to be copied to, all the HDFS data had to be copied to cloud. So this was needed because there were different types of users, teams that needed this same data to be consumed by different Google data products. So we couldn't just keep them on-prem. And disaster recovery was also an additional gain from this. Then the second approach was that the ad hoc compute and the data was split. So with regards to moving compute to cloud, the approach we took was that we would split data and compute. So that would allow flexibility to scale both these components independently. And it would also allow us to work and develop and migrate both these components simultaneously, compute as well as the data. And the third approach was Hadoop stack upgrades. We had to, like I explained in the previous slide, the stack had to be modernized, and we needed privacy and data protection, full support for privacy and data protection. And the thing to note here is that these three were not worked on separately, but simultaneously. So this approach was, all these three approaches were worked on simultaneously, which helped us save a lot of time in bringing up the cloud clusters and working on them. So next we'll explore challenges we experienced around a few areas, like moving our on-prem data to the cloud, ensuring proper security paradigms were in place without having to change our on-prem security systems and tools, and in streamlining cloud deployments for speed, agility, and consistency with on-prem cluster configuration. So with regards to data, one of the main challenges was moving the volume of data, which is 300 petabytes, which was 300 petabytes at that time when we started. So it's not, and this 300 petabytes is it's logical size. It's not the replicated size. So moving that much data would require a high bandwidth usage, and so to that end, we worked with Google and we picked up on their direct peering options, and we actually set up a private, something called a private network interconnect, which is a private peering connection, and it's a direct connection between our network and Google's network for exchanging high throughput traffic. So that was worked by the network engineering team, and it was between, so that was one of the first things that was ensured between the Google network and the Twitter network. And it started at 800 Gbps, and now we are around 1200 Gbps. So and the storage of data, that the data sets were actually put in are actually put in GCS buckets, and these are also, even for HDFS data, or data required by Hadoop and MapReduce, it's not in local disks attached to the worker nodes in Hadoop clusters. And we achieved this by leveraging the Google Cloud Storage Connector, which is a tool provided by Google and is open sourced. So if you check for that, and it's in the resource pages down. So for our usage, it has been adopted with some customization to fit into the file system abstraction used by our data platform tools, particularly Hadoop. So let's take a look at the file system abstraction now. So this is how it is on-prem. Typically, when you have a HDFS cluster, the file system access is, or the file paths are specified using HDFS:// then the cluster name node name and a port, and then the directory. So like we have two types of data: logs collected from events, and then there are user data. So after the name node, the information, you would have either a logs directory or a user directory, and under that a log category or a user directory, particular username. So when we started implementing federated HDFS, the normal HDFS protocol wouldn't be valid anymore. So VueFS had to be used, and in VueFS, the path is shown, or his path is used in the second line, as shown in the second line, where you would have users, then the cluster name, and then the directory, logs or user, and then a log category or username. And to make it easier for our users, we have customized our Hadoop clients so that when users, so that allows users using our Hadoop clients to specify paths in the format shown in the third line. Like there's /data center, then cluster name that will belong to that data center, and then logs or user and username or log category. So now let's look at how this same data sets are accessed in the, or needed to be accessible in the cloud. So the Google Storage Connector with customizations has allowed us to match accessing data sets in GCS buckets to the way we mount HDFS directories. So like you shown, the basic or the way GCS buckets are represented as GS colon, then it's a bucket name. And as you all know, Google Cloud doesn't have, or buckets don't have the concept of hierarchies or trees. So what we came up with a naming convention for the bucket that would allow or make it easier to identify whether it's a log and a category or a user and a username. So it would be logs.log category or user.username, and then logically you would add other components. So on-prem, the connector path would be /logs partly cloudy, based on what we've seen in the previous slide. So in GCS, so the actual resolved path based on the customizations done to Google Storage Connector would allow us to map /GCS /logs or /user and then the log category or username into the cluster. Into the client. So whoever is using our clients, Hadoop clients, could easily access it like that. So the advantage is other data platform users could also leverage our Hadoop client and access these paths like this. So this made it possible for our users to migrate their jobs to GCP clusters using the same code base they use for on-prem jobs. So that's with regards to data. And then let's look at some of the challenges we had to overcome on the security front. So this is like a broad view of how on-prem and Google Cloud clusters would interact. So this is like a bird's eye view of the Twitter environment right now. So in the Twitter data center shown on the left side, in the red box, you can see there are the Hadoop cluster components, the zones and all those things. And in the right, you have two boxes. And essentially, instead of setting up one single big Google cluster, based on the leading users of the data, we divided the clusters into multiple projects so that in each project there would be a single cluster. And inside the clusters, you would have, the clusters using GC compute, the nodes, worker nodes, resource managers, name nodes, all those things. And then you had data in the GCS bucket. And each GCP project has its own VPC, virtual private cloud, with subnetworks for separation of edge and internal connections. So there is an internal subnetwork and there is a subnetwork for specific nodes that need edge connection, that is connections from the Twitter data center. So these are exported, Abhishek, go back. So these are exported from a centrally managed project into these cluster projects, the network configuration, VPC, all those things. And the firewalls are denied by default in and out of projects with specific allowed connections. And another thing is that UIs, users will have to access name node UIs or resource manager UIs to view their applications and all those things, the status of their applications, jobs, those kind of things. And because of these, we are setting up Kerberos clusters and we were setting up firewall rules that were very restrictive. We implemented Nox proxies within the projects, GCP projects, that could act as the front end for the resource manager UIs and the name node UIs. So that would prevent users from being able to, or having to directly access or give privileges for them to directly access any of the nodes inside the GCP compute cloud. The restricted shell access was also implemented. We implemented nest boxes that for users having to run their jobs and for administrative tasks. So let's move on to the components in a project. Broadly, these are the components in a project, GCP project. So as I said, there's the GCS buckets. These buckets can be accessed by other products as well as monitoring and logging. Then within the clusters, you had different type of compute nodes. And we are setting up Kerberos clusters, and these Kerberos clusters secure connections between each component service in the cluster using Kerberos authentication and authenticates users who are running jobs. So this is managed using a custom developed IDM service that we worked with Google to develop it, but it was we worked on it and they worked on it. We needed to share some work based on that, but it's customized for us. And key tabs are distributed using our own. The key tabs are an essential component to ensure Kerberization works. So those are implemented or distributed using our own secrets management service. I will talk more about this in the next slide. So as mentioned earlier, As mentioned earlier, we widely adopted GCS connector to provide an HDFS compatible API, so users could migrate their jobs and applications without code change. It also allows us to keep data in GCS buckets for usage by other tools and products in Google's data platform ecosystem. Now, given the volume of data Twitter handles, data retention and scrubbing PII, personally identifiable information from this storage needs to be proper, and it has to be automated to work efficiently and at the scale. So that is where SDRS, which is supplementary data retention service, that comes in. And it's also another product or feature that we worked with Google and developed, and then we have open sourced it as well. So it's basically used to ensure data retention policies are enforced based on our unique requirements. And our retention policies cannot rely just on object creation information stored in GCS object metadata, which is what Google's object lifecycle management feature uses. So that wouldn't work for us. So that is why SDRS was implemented, and it helps, or it allows removal of data based on creation time that is encoded in the partition prefixes itself. So the partition names would have the data creation name, and we can write the retention policies based on that, and SDRS will scrub the data, remove the data, and do stuff like that. Now, yeah. So because of our customized authentication access requirements, we needed a custom identity management service. But there are inherent risks associated with having a single overreaching service, that manages all access and authentication requirements. So what we did is we designed multiple services that manage subsets of identity and access management requirements. And the single bubble shown there as the IDM service is actually multiple services running asynchronously, performing various actions. And as we've already mentioned, different teams or users that uses these services have different cloud projects, and in each project there is one bucket per log category, right? And per user also. So, and the data set used by Hadoop and the other services like BigQuery, CloudML, Spark, these are all in those buckets. So then there is also the requirement of Kerberos based authentication and GitHub management. So essentially what we have a service that manages buckets, the creation of buckets, applying ACLs based on Google accounts. Then there is another service that makes Kerberos authentication possible by mapping on-prem POSIX accounts to shadow Google accounts. So, and the shadow Google accounts will have privileged or access to the key tabs required for that account to ensure Kerberos works. Then another service performs the Kerberos key tab distribution based on these shadow accounts configured and key rolling and management. Then there is another service that actually manages LDAP mappings to enforce authorization on GCS buckets on within the machines and all those things. So next we'll talk about some, that brings us to the end of security challenges that we're talking about. And next we'll move on to some of the deployment challenges we overcame. So in the deployment phase, one of the main things was that configuration had to be consistent between on-prem and cloud clusters. So for that, we needed refactoring of Puppet by introducing a new profiles, role, module, organization of the Puppet code. And we moved to a data-driven using Hiera, a data-driven approach that uses Hiera to store a lot of the config information instead of having to hard code it in the manifest. Then a lot of testing and validation was also included to ensure that we could quickly adapt to changes and we could quickly make modifications and ensure that the modifications would not break anything. So we had to reconcile Puppet code that had been built over several years to satisfy all these conditions. And we started with separate repos for cloud and on-prem, gradually transitioned to a unified repo that is using the data-driven approach, using that would have Hiera store the information required to configure machines based on where the services are running, what services are running, and which environment they were in. Not just the Puppet environment, but also the cloud or data center, on-prem data center, that environment as well. Another challenge with regards to deployment was that we needed to quickly deploy clusters with up to 3,000 nodes. And for this, we had to leverage Google Cloud Deployment Manager. So within the cluster itself, there was a challenge of having to deploy various types of instances, and in each type had to be of varying quantities. And for resource managers, we know a certain combination of memory, CPU, and all those things, cores, all those things that will work well. For name nodes, we have a slightly different combination. For worker nodes, we again have a slightly different combination. So we needed to quickly bring up clusters that, or even configure all these clusters, deploy all these machines quickly and efficiently, and it had to be a scalable model. So we developed a tool in-house that actually ensures Hadoop cluster deployment automation with auto generation of Cloud Deployment Manager template and resource definitions. And it's a Puppet-based tool that creates these templates and config for clusters. And the tool allows us to quickly generate cluster resource configurations and push them to the CDM API endpoint for deployment. And one of the advantages of using Puppet here is that it allows us to use Puppet's own inherent features to code the generation of the required files. So it's not like basically you look at Puppet, it works on help, or inherently it has a lot of features that allows us to generate these kind of YAML files or whatever we need based on the data it can merge or pick from a lot of configuration files or different configuration locations. So that has been one of the main advantages with regards to using the tool for and that has helped us in reducing the deployment time of these clusters and ensuring that the clusters are deployed with all the components present in them. Yeah, so I guess that brings us to the end of our talk. So some final thoughts that we would like to leave you with. So this undertaking, so basically the partly using the partly cloudy undertaking, sorry, has allowed us to make it possible for data platform users to leverage the most latest technologies and tools while keeping the data access model simple. And partly cloudy has put us in a position to implement and build on business continuity for data platform services. And it has allowed us to put in place a robust Hadoop cluster architecture, which is secure and is running up-to-date components. So yeah, thank you. And these are some of the resources we have referenced in this talk. And yeah, I mean, we are now open to questions.
Okay, thank you, Abhishek and Jeffrey. We have two questions so far. So the first question is from Vijay, Vijay. So as IDM service is a gateway of security, how you will manage fault tolerance?
I mean, see, this is the service has been inherently designed in that way. It's not like I said, all these it's not one single service. There are several services, and they are not they're scalable, designed to be scalable, and what can I say? It's following all the microservices, all those kind of design concepts. And on-prem also the Kerberos servers, all those things. These are all scaled, following the scaled model. So, is that satisfactory?
Vishwa, let us know if that answers your question. Meanwhile, let us move on to the next question. It's from Venkatesh. So one of the reasons for moving data to cloud is to leverage cloud infrastructure services, which includes hardware as well.
Yeah.
In this case, Twitter is trying to use its own hardware in GCP infra, or what is the major benefit we are getting from this migration?
Yeah, like you said,
or any other benefits? Sorry.
Yeah. Oh, sorry. We are not using our hardware. We are leveraging GCP. So the compute nodes are not our hardware. It's GCP instances itself. Sorry, GC instances itself. They are GC instances, and the images that we use or the instance types that we use are from Google's offering. It's just that Google had better offerings that would satisfy our needs or based on the tunings or the learnings we had from running Hadoop over these years. So it's in that way we are using Google's own infrastructure itself. And like, so business continuity, scalability, all those things, aspects that are inherent to the Google Cloud are also inherent to this model itself. It's just that, we look at, or we wanted certain types of instant types. The images, obviously, everybody does it. Like, OS images are all, we have only a specific subset that we use, and they need to be Twitter approved. But again, that is also part of every cloud infrastructure or cloud any more company running cloud models. So like I said, the major benefits is one, like we said, business continuity, easily scalable, more even the hardware requirements, like you said, if we need like maybe to set up a new cluster quickly, rather than on-prem, cloud affords us that advantage now. Then data separation was a major factor there. It's a major component there. And another thing is we are able to utilize Google's latest data platform, services like, as we said, BigQuery, CloudML, and there are several other users also. And all those things we can now leverage and provide it to our users without having to, set these up and manage them as multiple components for us.
All right, Venkatesh, let us know if that answers your questions, or if you have follow-up questions, please do ask. So meanwhile, the third question is from Jay Ganesh. Is there a specific reason why you are using Heron built on top of Storm? Also, in Twitter, are you using Apache Flink for real-time analysis?
So Apache Heron was, as I already mentioned, the successor of Apache Storm. There were a couple of things that we did see in terms of performance. I think we also have a detailed paper on that. I can share that on the chat. But long story short, we did see a reduce in hardware footprint when we tried using Apache Heron. That is kind of tightly coupled with our infrastructure, which is Mesos that we use on the compute side. So yeah, that helped us reduce our hardware footprint by a couple of, by a large value. And having said that, we had higher throughput as well. So it was a win-win, and yeah, that's the reason.
All right. That's all the questions we had. Anything else? Jaganesh, does that answer your question?
Yep. So I also need to know whether you guys are using Apache Flink, or is the Apache Heron is the only real-time streaming analysis source you are using?
I have seen folks using, because we don't really work on the real-time systems as such, but yeah, we have seen a couple of repositories using Apache Flink. So yeah, we do use a good mix of both, but majority of the technology that we use for real-time streaming is Apache Heron. We were a long-time users of, I think we've used Apache Storm more than anybody else, but we kind of hit performance issues as we wanted more performance for our scale. So yeah, then we moved on to Heron, and we also use a bit of Apache Flink. It depends on the use case. Yeah.
Yeah, thanks. I just was figuring out which was the best to use in different scenarios. That's it.
Oh, okay. All right. So that concludes our questions. If any more questions, feel free to ask here, or tag us on LinkedIn. You have seen the post, or meetup.com, wherever you want to, and we will answer those questions offline. So thanks, Jeffrey and Abhishek, for the wonderful talk, and thanks the participants for the question.